Part 2 of this presentation covers the analysis of variance and the importance of reviewing the data in preparation for this analysis. Statistical variance is a measure of how spread out the data is about its mean. The goal of AOV is to dissect the variability in the recorded assessments, to understand whether the differences we have observed between treatments is due to the treatment itself, or just by random chance. There is controlled variability that the researcher had a hand in, from the treatment and blocking structure. Then everything we cannot control is called the experimental error. The overall approach is to consider that the observed response has three components: the baseline response if nothing had occurred in the trial, the effect that the treatments and blocking specifically had, and the effect of random influences too. In order to draw conclusions about the treatment effects, we want to estimate what the random or uncontrolled effects are. To do this, we're going to need to make some assumptions about their behavior. It turns out that these assumptions are quite important, because if they are not met, then the results of the analysis cannot be relied upon. So these assumptions of AOV become a key focus in data review. Let's take a closer look at them. The first is homogeneity of variance, that the variances of the different treatments are approximately equal. If a treatment is much more variable, or much less variable, than the others, the analysis will not work. So to determine if this is the case, we can look at a box whisker graph and run a test for homogeneity of variance. Levine's is generally chosen, but Bartlett's is also an option. The next assumption is that the distribution of errors is normal, or bell-shaped. If we have this and equal variances, then the math can do its thing, because we can calculate a reasonable guess for the amount of error based on the standard bell-shaped curve. Tests for this include skewness, kurtosis, and Shapiro-Wilks. The other two assumptions are harder to test for, but should still be considered, especially during trial design. The first one of these is additivity of treatment and block effects. For example, the effects of insecticide treatments are likely to be multiplicative on the population count, affecting a proportion of the insect population. So a more suitable assessment to analyze efficacy would be a % of untreated calculation instead of raw counts. Finally, the last assumption is independence of errors. Rating does not directly impact the next or previous value. The key is to not introduce bias in the assessment, like edge effects or subjective ratings performed inconsistently. The assessment map may be useful to detect some of these potential issues. What happens if these assumptions are not met? We cannot rely on the results, unless we take alternative action. There are data correction transformations, designed to correct the underlying distribution of the data, and thus the error, without affecting the results. The logarithm transformation is used with counts of things that occur in clusters, a log-normal distribution. The square root transformation is for counts of things that occur at random or rarely, following a Poisson distribution. The arcsine square root % transform works with proper percentages that often follow a binomial distribution. Spatial models try to recover information about hidden variables across the field. There are 3 trend and 4 nearest neighbor models that can be used in ARM. This is commonly used when the blocking design fails, or when blocking is not a realistic option. Non-parametric statistics throw out AOV and its assumptions, and instead analyze the data by ranking the assessment values. A mean comparison test can still be run on the mean of those ranks. Learn about the column diagnostic tool in ARM that is used to test for and resolve these issues in the data review tutorial. After reviewing the data, we are now ready to perform the analysis. Here is an example AOV output, from a trial with 5 treatments and 4 reps. Let's go through each calculation. Degrees of freedom is a bit tricky to define, but is the number of values in a final calculation that are free to vary. For variance, the degrees of freedom is n-1, 5 treatments you have 4 degrees of freedom. The sum of squares represents the amount of variation in the data, split up into each source listed in the table. The mean square is the sum of squares divided by degrees of freedom. We are taking the amount of variation and dividing it by the degree to which it can occur. Then we calculate an F ratio, which indicates the level of variation from that source, compared to random variation. The larger this ratio is, the more likely that variance from this source is not due to just random chance. To quantify this, we calculate a p-value, the probability that observed differences in treatment means, or block means, could have arisen by chance. A low p-value, typically less than 5%, indicates that we can be confident that there are real differences among treatments. Whereas a high p-value, like between blocks, indicates that there is no evidence of a real difference among blocks in this case. This could be because there is no real difference or that the differences are too small to detect. To summarize, the AOV analysis breaks apart the variance of observations into sources, then calculates a p-value as the result. Remember, a p-value is a probability. The AOV p-value is the probability that no differences in treatments exist. So a p-value of 0.04 means we are 96% confident that there are significant differences between treatments. But we are not done yet. We need to know which observed differences between treatments are significant and which are not. We cover mean comparisons in the next section.